Question 5 now. A battery shown here with negligible internal resistance, which is good news. We know it has an EMF of 9 volts. We have two resistors. We have a 120 ohm resistor there, and we have a 60 ohm resistor there, forming a potential divider. But first of all, they say, what's the current flowing in the circuit? Well, total resistance is just those two resistances combined, 120 plus 60, which is 180 ohms. Now I can use Ohm's law for the whole circuit. I equals V over R, which is 9 divided by 180, and I have a current of 50 milliamps. That's 5 times 10 to the minus 3 amps. But I'm using that prefix to get rid of the times 10 to the minus 3. Calculate the voltage reading on the voltmeter. Well, let's look at these two resistors. This one is half the size, so it will have half as much PD as that resistor. So if I do 9 volts divided by 3, that gives me 3 volts is 1/3. This gets 2/3, 6 volts. This gets 1/3, 3 volts. So it's just going to be 3 volts. If you prefer to work out a little more formally, I could say, well, this gets 60 out of the total 60 plus 120. So that's its proportion of resistance. Multiply that by 9, and that will give you your answer of 3 volts. So that's the resistor over the total resistance times the PD will give you that value. The next part, I've, as you can see on the left, just scribbled what this circuit will be. It says the circuit shown is a potential divider. It's now modified by replacing R1 with a temperature sensor. That's going to be a thermistor, and it even tells you about its temperature coefficient. It says its resistance decreases as the temperature increases. So now what's going to happen to the reading on the voltmeter as the temperature increases from a low value? So as the temperature increases, what's going to happen to the resistance? Well, it tells me that that means that resistance will decrease. So that's the first point. This resistance is going to decrease. Therefore, I can say that the total resistance in the circuit is going to decrease. And that is worth a mark. Because the total resistance has decreased, I can say that the current will increase for the whole circuit. That's also worth a mark. Now if we look at R2, think about Ohm's law for R2. I equals V over R. We're saying that the current increases for R2, but the resistance stays the same. Therefore, the PD across R2 must increase. That's the answer we're looking for. Now I could do this in an alternative way. What I could say is as the temperature increases, the resistance of the thermistor decreases. Therefore, R2 has a bigger share of the total resistance because it's now significantly bigger than that thermistor's resistance. It gets a bigger share of the resistance, and therefore it gets a bigger share of the 9 volts. That's another way of arguing it. Question 6, looking at a little bit of AC current. So here is an oscilloscope screen. They tell you the readings, the settings. We've got 1.5 milliseconds per division as a time base and 1.5 volts per division as the Y gain. They want you to calculate the frequency. Frequency is 1 over the time period. Now that is not on your formula sheet, but you should know that from the particle side of the course anyway. Frequency 1 over time period, so I need to know the time period. Now if I look at the time period from there to there, I can see that it's 1, 2, 3, 4, 5, 6 and a bit divisions. Now that's quite difficult to measure accurately. So what's far easier is to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's easier to say that 10 divisions is 1.5 cycles. And so then I can do 10 divisions times 1.5 milliseconds per division, which is 15 milliseconds. That's equal to 1.5 cycles. And then it's really easy to say, therefore, my time period is equal to 10 milliseconds. Let's put that in here. Frequency is 1 over time period, which is 1 over 10 times 10 to the minus 3. That gives me a frequency of 100 Hz. Hertz. Put that answer there. Nice and straightforward. Now it's far easier with the peak voltage. I can see the peak voltage is exactly 2 divisions, so it's going to be 2 times 1.5, which is 3.0 volts. Really easy to calculate the peak voltage. Then from my formula sheet, I write down the equation that Vrms equals V naught over root 2, straight from the formula sheet. Nice and easy. So all I need to do is plug in my number 3 over root 2, that's worth a mark. And then write down the answer, which is 2.12 volts, and that's worth the second mark. State and explain the effect on the oscilloscope trace if the time base is switched off. Well, I can say that the trace no longer moves horizontally, and so I will not get any horizontal effects, but I can also say that it will move up and down, and it'll go from plus 3 volts to minus 3 volts. So it's going up to the peak and down to the negative peak. And so that will draw a vertical line on the screen. 2 marks for that. And job's done.